going to discuss the problems which are solvable by using Poisson distribution as well as binomial distribution. Okay, so last two previous problems we saw that only by Poisson distribution. See here it is. If the probability that an individual suffers a bad reaction from a certain injection is 0.001, determine the probability that out of 2000 individuals, exactly 3, more than 2 individuals, and third one none, and fourth one more than one individual suffer a bad reaction. Okay, so here it is. See clearly, if the probability that an individual suffers a bad reaction from a certain injection, suppose someone went to hospital and they give some injection for the disease. Okay, so due to that injection, okay, some reactions will come, right? Some bad reactions came. Okay, so for getting that bad reaction, what they are saying the probability. Okay, so 0.001 possibility is there for getting bad reaction from a certain injection. Okay, so because of this what they give the injection, because of that injections some reactions came, so that reactions, the possibility is here 0.001. Okay, next, determine the probability that out of 2000 individuals, okay, it means total number of individuals, how many are there? 2000. So this is probability p, we can say that, and this is number of individuals n they give. Now they are asking to calculate the probability exactly 3, so that is nothing but p of x is equal 3. So this is first one, exactly 3, and second one more than 2. So more than 2 is nothing but, so more than we are giving representation as greater than, so that is nothing but simply we are writing p of x greater than 2. And next none, so none is nothing but simply what we can write, x is equal 0. And next more than one individual, so more than is nothing but in place of this one simply what we can write, greater than, so x greater than 1. Okay, so suffer a bad reaction. Okay, so this is the information they give. So previous what we solve the problems, directly they give average, so on an average these many of people suffering for that, so like that they mentioned. But here it is, they clearly mentioned here p value as well as n value. So for getting the lambda value, so what we require, n and p. So lambda is equal to n into p. So simply we can multiply 2000 into 0.001, and next exactly 3. So these things we can calculate if we are using Poisson distribution, means simply what we can apply, p of x is equal to simply what we can write, e power minus lambda power x by x factorial. So that is the one we are applying, right? So e power minus lambda power x by x factorial. So this one we are using. Okay, for applying Poisson distribution. Why we should apply only Poisson distribution? If you observe in previous problems, some in the problem somewhere they mentioned they distributed as Poisson variations or Poisson variable, or we are taking Poisson distribution, like that they mentioned. But here it is, they didn't mention anything. So what we have to apply, whether Poisson or binomial. But based on the conditions, what we are saying, the conditions of Poisson, n should be very large. See here, n is equal to how much? 2000. Okay, so 2000 individuals, and p is here 0.001. So when we discuss the conditions of Poisson distribution, what we said, n should be very large. Okay, so n should be large. Okay, so n is large and p is very small. So those things we said. So for applying Poisson distribution, n should be large and p should be very small, which is nearer to 0. Okay, which is nearer to 0. So here it is, if you observe this one, n is large and p is also very small, 0.001 possibility for getting a reaction from a injection. Okay, so that's why we are applying Poisson distribution here. Okay, so suppose if you don't know how to what we have to apply, you can apply binomial as well as Poisson. But for applying binomial distribution means what we are using binomial distribution, NCX. So this is the one we are applying, NCX p power x q power n minus x. So p power x q power n minus x. So this one we are applying, right? So NCX p power x q power n minus x. N already we know that 2000, and p also we know that 0.001. But what about q? So we'll get it as q simply 1 minus p. And x is nothing but what they asked here. So put x is equal to 3. But C calculation. So for calculating first problem, what we have to do it? 2000 C3, right? N is 2000. So for that 2000 C3, and P is nothing but 0.02, and whole power x is nothing but whole power 3 for first column, and 1 minus P is nothing but 0.02 whole power n minus 3, that is 2000 minus 3. See how much big calculation we have to do it here. 2000 C3 0.02 whole cube minus 0.02 whole power, so 1 minus 0.02 whole power 2000 minus 3. So this much of thing we need to apply for applying binomial distribution. Okay, so for that here we are applying Poisson distribution. So generally by seeing that n is very large and p is very small, we have to apply Poisson distribution. Okay, suppose you don't know, so exactly what you need to apply. So you know the value of n and p value, we know that. So obviously you can apply binomial also. Okay, so this is the one. So that's why we are discussing these problems again. This is not a new one. What we discussed problems last class, same as is those problems only here also we are discussing. But for saying that variation, so there it is just average lambda value directly they give. Suppose if they don't mention these two and directly they give lambda, then there is no alternative, we can apply Poisson distribution. But here it is n value they give, p value they give. So that's why you can apply binomial as well as Poisson. Okay, so next let us see the and remaining simply given probability. So what they gave in the problem, simply we wrote here p is equal 0.01001 and n is equal 2000 number of individuals, and lambda is equal, so mean we are calculating. So lambda is equal to how much? N into p. So n is 2000 and p is 0.01. So by multiplying those two we are getting as 2, and don't forget it, lambda must be greater than 0. And here it is, we are applying Poisson distribution. So Poisson distribution we are writing as p of capital X is equal small x is equal e power minus lambda power x by x factorial. So here it is, x is nothing representing successes, those x are 0, 1, 2 and so on, and lambda must be greater than 0. Okay, now we are going to solve the problems what they asked in the problem. Okay, so first one what they asked, more than 3. So sorry, exactly 3. So for that, exactly is nothing but what we are using, equal to. So in place of exactly we wrote here equal to, and 3 mentioned, so 3 as this. And here it is, lambda we got it, lambda is equal to 2. So for that in the formula we substituted in place of lambda is 2, so 2 here, and here it is in place of x as 3. So for that 3, and 3 factorial is nothing but 3 into 2 into 1, so 3 into 2 into 1, so that is nothing but 6. So for that 6 we wrote here, and by using cancel we got the value 0.1804. So this is the probability, this is the possibility, this is the chances for getting certain reactions from a certain injection. Okay, bad reactions from a certain injection. Okay, more than 2. So more than is nothing but simply what we are writing, greater than. So here it is. So you can apply this one, 1 minus p of x less than or equal to 2. So this one I applied by using sum of the probabilities is equal to 1. It means, so that is P of x less than 2 plus P of x greater than or equal to 2. So P of x less than or equal to 2 plus P of x greater than 2. P of x greater than 2 is equal 1. So by using this, here it is they asked more than 2. So this one they asked. So for that we are taking this one into right hand side. So here it is having plus, when it goes to that side it changes to minus. So 1 minus P of x less than or equal to 2, and we can simplify. Or you can apply the same thing in another words, since we know the value of n here. So n is equal to how much? 2000. Okay. So 2000 n. So P of x greater than or equal to 2. P of x greater than 2 means, so 3 onwards you can calculate. P of x is equal to 3 plus P of x is equal to 4 plus P of x is equal to 5, 6, 7, like this, until how much we need to calculate the probabilities? 2000. Okay. So I think 30 pages or 40 pages. Okay. 2000. So up to this one you can calculate. Okay. Either you can follow this or you can follow this one. Okay. Any one of that you can follow. But this is a time taking process. That's why we are using this one. So, and binomial distribution means for applying x is equal to 3, 4, 5, 6 and so on 2000 in a sense. It takes 3 hours or 4 hours or 5 hours also it takes time. So for avoiding that purpose, we are using here Poisson distribution, and simply we are writing P of x greater than 2 as 1 minus P of x less than or equal to 2, and here it is x less than or equal to 2 means here it is 0, 1, 2, up to 2. So that is P of x is equal to 0 plus P of x is equal to 1 plus P of x is equal to 2. So since P of x is equal to, we know that we are applying Poisson distribution. So for that P of capital X is equal, small x is equal, simply what we are using, e power minus lambda, lambda power x by x factorial. So e power minus lambda, lambda power x by x factorial. So this is the one we are applying. So here it is, in place of x we are applying, so in place of x 0, and in this in place of x as 1, and in this in place of x as 2. And already we know that the value of lambda we calculated. So lambda is equal to how much we got it there? 2. So lambda we have to substitute 2, and in place of x is 0, and lambda is equal to 2 in place of x as 1, and next lambda is equal to 2 and in place of x as 2. So like this we need to substitute here. Okay. So by substituting we get the value of the probability which is more than 2. So simply we substituted, in place of lambda is 2 and in place of x 0, 1, 2, like that. So we got it as here 0.3233. Just for seeing the variations for between binomial and Poisson, we are solving this. Okay. So nothing new we are solving in that. Okay. Next, third one, none. So none is nothing but P of x is equal to 0. It means what is the possibility for getting not in reactions from certain injection. Okay. So here it is, simply e power minus lambda, lambda power 0 by 0 factorial, and this value is nothing but 1, since 0 factorial is 1 and anything power 0 is 1, and remaining e power minus lambda, since lambda is equal to 2, so we substituted in this, then we got it as here 0.135. and next fourth one, P of x greater than 1. Are so what they mention in one notation, more than. So more than means what we can use, greater than. So here it is, in one notation more than, or simply greater than. Okay. So more than they can give, or in place of more than they can give as greater than. So more than is nothing but greater than. So that's why we write here greater than. Here also same thing, like as previous one. You can write 2, 3, 4, 5 and so on up to how much we can calculate 2000. Okay. So up to this one you can calculate, or simply you can write 1 minus P of x less than or equal to 1. So x less than or equal to 1. So it means equal to 1 and less than 1. So less than 1 is nothing but 0. So in the formula we have to substitute in place of x as 0 and in place of x as 1. Okay. So in this we substituted in place of x as 0 and here it is in place of x as 1. So lambda power 1 by 1 factorial. So now we are simplifying this. 1 minus e power minus lambda is the common one and already we calculated. So lambda is equal to 2, that one we substituted, and here it is, this is 1 plus lambda. So lambda is nothing but 2. So simply what we get it, 1 plus, so 1 minus 1 plus 2 is nothing but 3. So 3 into e power minus 2. So by using calculus you can find the value of this one. Okay. So 1 minus 3 into e power minus 2. How much we got it? 0.5939. Okay. So nothing new we did here. Just we applied Poisson distribution formula. Same problem we can solve by binomial, but it takes a lot of time for doing calculations. Okay. So that's why for seeing the variances between binomial and Poisson, we are solving these problems. Okay. Next, same the type of one. A manufacturer knows that the condensers he makes contain on an average 1% defectives. He packs them in boxes of 100. What is the probability that a box picked at random will contain 3 or more faulty condensers? Okay, so it means that suppose you are the manufacturer, you are manufacturing some products. Okay, so you already know that whatever you are manufacturing, okay, that obviously if you are manufacturing 100, 1 or 2 will be defective. Okay, in the same way, here it is, he already knows that whatever he is manufacturing, so what is manufacturing? Condensers. So condensers he is manufacturing. So in that, on an average how much defective one? 1% defective. It means if you are taking 100 items, in that one item will be defective one. So he is only saying that what a manufacturer is doing. So total how much? N defective items. In that, sorry, N total items they are manufacturing. In that defective items are 1 defective items. It means the possibilities for defective items is P is equal to how much? 1%. So P is equal 1% and N is equal to how much? 100 defective items. So N is equal to 100. Okay. So N is equal to 100. And next, he packs them in boxes of 100. What is the probability that? So probability they ask that a box picked at random. Okay, so randomly picked a box will contain 3 or more faulty condensers. 3 or more is nothing but P is nothing but probability and 3 or more. So that is nothing but 3 or more. Okay, so 3 also they included. So for that P of x greater than or equal to 3, we need to calculate. So why should we apply Poisson distribution? See that n is equal to how much? 100 and P is equal to how much? The possibility is very very small. So P is equal to how much? 1%. Okay, so 1% is nothing but 1 by 100. So 0.01, which is nearer to 0. So 0.01. So n is large and P is small. So for that we need to apply Poisson distribution. Okay. So for applying Poisson distribution, what are the conditions we are saying? N should be large and P should be small. Okay. And we are going to calculate P of x greater than or equal to 3. But here they didn't mention anywhere Poisson. So if you want, you can use binomial also. But it takes a lot of time for doing calculations. Okay. See here, that one only we mentioned. Given that probability of defective condensers P is equal to how much they go? 1%. So P is equal to 1%, 1 by 100, 0.01. Okay. Now total number of condensers N is equal to how much they go? 100. Okay. Mean. So we are applying Poisson distribution. We require the value of lambda. So lambda is equal to n into p. So 100 into 0.01, so which is equal 1. Okay, now we are going to apply Poisson distribution. So here it is, p of capital X is equal small x is equal e power minus lambda, lambda power x by x factorial. So we are going to calculate p of x greater than or equal to 3. So that is simply what we can calculate here. So p of x greater than or equal to 3 means, so we can write simply 1 minus p of x less than 3, or x greater than or equal to 3 means, so p 3, 4, 5, 6 and so on up to what we have to calculate 100. Why? Because n is equal 100. Or like this also we can calculate 1 minus p of x less than 3. Okay, so here it is, p of x is equal to 0, p of x is equal to 1 plus p of x is equal to 2. So e power minus lambda, lambda power 0 by 0 factorial. Simply we are substituting the formula e power minus lambda, lambda power x by x factorial. So e power minus lambda, lambda power x by x factorial. So in place of x we are substituting 0, and in place of x as 1, and in place of x as 2. So these are the three we are applying here. So x is equal to 2. Okay, and already we know that the value of lambda, so lambda is equal to 1. Okay, so that is lambda is equal to 1 we substituted. So by substituting here we got it as here, in place of lambda as 1, and next here it is lambda power 0 by 0 factorial is 1, and next lambda power 1 by 1 factorial is nothing but lambda. So lambda value is 1 and 1 by 2. By simplifying that we got it as 0.0803.